Welcome group to the next video in chapter 2. This is just an extension of area, and we're looking at perimeter as well. In this section, it's not so much the calculation of area alone, it's the best area or optimum area and perimeter. So this is really practical, and there's some good applications in these two problems that we're going to look at. This will be done in class, so if you're seeing this video, you may have already completed these activities. The two scenarios are constructing a garden from 24 1-meter sections of edging, trying to find the maximum area that can be enclosed. This is found on pages 87 and 88. The second scenario is the construction of a rectangular patio with square patio tiles. And here we're trying to find the minimum perimeter the patio can have. And both of them are going to involve constructing a table of values and as well as a graph. We will be using the graphing calculators as well, and in this video I'll show you how you can use a spreadsheet using Microsoft Excel to make graphs and also calculate values for us from a table. So let's get started. In the first problem, we'll go back. We're looking again at finding the maximum area that can be enclosed with 24 1-meter sections. So let's just consider some simple formulas that we're using already. Area is length times width, and if we know the width, or if we know the length rather, and we're trying to find the width, then we would be using actually the perimeter. So in this case, another formula that we need to remember is that the perimeter is twice the length plus twice the width. So a visual of a rectangle, which could be a square, it could be different in its dimensions, is width and length. And again, typically I label them where the longest side is actually the length. However, once you decide that side number 1 is going to be called the length in this activity, stick with that and try to generate a full table of values even when the L value gets smaller. Alright, so if the length was 1 meter, then the width would be unknown, but we do know that the perimeter in this case is going to be 24. So if the perimeter is 24, then we have a simple relationship here, which is that twice the width plus twice the length equals 24. So 2 times the width plus 2 times 1 meter in the length would be 24. So that gives us 2 times the width would be 24, subtract 2. So therefore the width would be 24 subtract 2 divided by 2. And this gives us sort of a general relationship that if we know the length, the width would be the perimeter subtract twice the length divided by 2. That relationship can be used regardless of what the lengths and perimeter values are. Perimeter subtract 2 times the length divided by 2. Make sure you follow order of operations. That's why I put the bracket around the difference between those terms before we divide. So let's see. This gives us at least one value in our table. We're filling in length, width, area, perimeter, and eventually we're going to get some ordered pairs from these values to make a graph. So the first value is shown here. When the length is 1, the width will be 11. I hadn't finished my math here, but 24 subtract 2 is 22, divided by 2 is 11. So that means 11 meter width and 1 meter length. The area would be 1 times 11, which is 11. And the perimeter is twice the width plus twice the length, which in this case it's constant. It's going to be 24 all the time. So I want you to fill in the rest of this chart. You have this handout, should have this handout, and then I'll reveal all the values that will be used for our graph. Alright, so here are my numbers. 2, 3, 4, 5, 6, 7, 8, 9, 10, and I went up to, I believe, 11. Can't have a length of 12 because that would use up all of the edging on the two length edges without having anything left for the width. So our maximum length would be 11, and that would give a width of 1. You'll notice that there's a lot of duplication in here. The original set 111 is repeated when we call the length 11 and the width 1. So we have a pretty easy time here to fill in all of our values. This will be 32, 27, 20, and 11. So there's repetition, and it's symmetrical, and we can see that in the table of values. The perimeter is constant at 24 all the way down. Okay, so that's just recognizing that for any given pair of values, if we were to take 2 times the width and 2 times the length, for example here, we would have 14 plus 2 fives is 10, so 14 and 10 would be 24. And that would be also, say if we use the 9 and 3 combination, that would be 2 nines is 18 plus 2 threes is 6, that's also 24. So no matter what we make the dimensions, we're using up all of the material. The perimeter will be 24. Now we can see in the table that our maximum area occurs at a value of 36 square meters. It occurs when the length is equal to the width, which would be our optimum, and that is a square shape. The ordered pairs here we'll use for the graph are simple enough, as long as we know what we're plotting. We're going to plot area versus length, which means that we want the area values to be the y and the length values to be the x. So our ordered pairs would be sort of over 1 up 11, and then over 2 up 10, and you can fill in the rest of them from there. So put in all your ordered pairs on your chart, and then we'll make our graph. Okay, so here are all my ordered pairs. Now what I'm going to do is going to open up Microsoft Excel here, and I have the data already preloaded, and we'll have a look at constructing our graph. All right, so if you have a spreadsheet software at home, it could be Microsoft Excel, it could be Corel Quattro Pro, depending, maybe you have OpenOffice, Sheets, whatever it's called. The difference between a word processing program and a spreadsheet is a spreadsheet puts all of your values into rows and columns, gives them column headers, which are letters of the alphabet, and then row labels, which are numbers starting at 1. So we can identify the location of a particular cell. That would be D2. And we see the location up here in the cell locator box. So if we want to refer to a particular location, we can just reference its letter and number combination. So now what I have here is I put my values in, and I just type as though I was in a word processor. Length, width, area, and perimeter go in the heading. I'm not trying to make this too fancy. It's hard sometimes to get the superscripts in here unless you go into adjusting the font. So we have the numbers, which is most important, just entering after each value 1 to 11, and as it turns out here, the widths are 11 down to 1. To calculate the area, in Microsoft Excel, you'd start with the equal sign, and then you would use the values that are already there. So rather than typing 1 times 11, I'm going to go over to A3, which is the first number, and I'm going to go to multiplication, which is on the keypad, and I'm going to multiply that by width. And I'm going to press enter, and it's going to give me 11. Now I have this formula up here. The formula bar here gives the same value, equals A3 times B3, and you probably saw that being filled in as I was typing. Now the nice thing about a spreadsheet is we can take that value, not 11, but we can take the way it was calculated as a number from the A column times the number beside it in the B column, and we can copy that, Control C, or you can use your menu, copy, and you can paste. And we're going to paste into all the cells that need areas. So I'm going to drag down here with my mouse, and I'm going to paste that. Okay, and you know what pasted is not only the numbers, but also the way in which they were calculated here. So we can see up in the cell editor here that that number there, 27, was A5 times B5, and all the way down we see how they were calculated. We can do the same thing for perimeter. Perimeter is twice the length plus twice the width, so we can say that perimeter is equal to, and now we're going to take 2 times, I'm going to move cursor over to the length cell, and I'm going to add 2 times, go over to the width, and there's my formula. 2 times A3 plus 2 times B3, press enter, do the same as before. I'm going to copy that into the cells which I need the values for, and paste them there. Okay, and of course they're all 24, but the important point thing is, like, I'm using the power of the spreadsheet to calculate things for me without having to do a lot of calculator work. Okay, now that we have the values, we want to keep in mind what we're actually going to be plotting here. So we want to plot area, these values here, and we want to plot them along with the length. So I'm going to press the control button now, and that's going to allow me to highlight a second column without having to worry about the column in between. Now I'm going to go over to the data menu at the top here, and as soon as that pops up, I'm looking for some kind of a graph wizard or a graph icon. I don't see that, so let's go to view here. Okay, how about insert? I think it's under insert. Yes, insert. Now what do we want to insert? We want to insert a type of graph. In this case, it says insert scatter XY. That looks good. There's different ways we can make it look. We want a trend line on this, so I would want one that has smooth curve. And there's no data points here. It's sort of connected with small line segments. It looks like probably this one here would be my best fit. So I pressed that. And before I did that, I had the option to select more. And if I go in there, there's all the values listed here. And it's not what I was searching for, but what I would like to do maybe is, in some cases, just take that graph and put it into a different worksheet. I've got my patio data down here. I could add another worksheet and put my graph in there, and of course if I wanted to print that, I could. Alright, here's my graph. I won't go into much more detail at this point about how to make the graph look nice. There's no really meaningful title on here, so I would have to go up and probably double click that, add a title. There are no axes titles, although they're scaled. I could probably change the way they're scaled by changing what the minimum and the maximum value are. I can do the same thing with the x-axis values. My data points can be adjusted a little bit, I'm sure, and so you play around with the different features of it. But the main thing here is we're able to get the graph. We can see that it's parabolic. It's an upside down parabola. If you've studied that before, you recognize the curve right away. It has a maximum. That's important too. And the maximum can be read off the graph as well. And I can click on a particular data point and see that that's 6,36. Go to this data point here and see that's my rectangle when it was length of 2 and area of 20. So here we're able to find the optimum value, and we're able to recognize that the area drops off whether we get smaller lengths or larger lengths from that point. Let's go back to the other scenario. Okay, so here we want to build a rectangular patio with 36 1 square meter patio tiles. So we'll assume they have an area of 1 square meter, but let's also assume that they are squares. So in this activity in class, we use little plastic squares, and we're fitting them together so there are no gaps, and we want to find the minimum perimeter that the patio can have. So again, here we're working with the rectangle, so our formulas are the same. We have length, width, area, perimeter, and some ordered pairs. If we choose a length of 1, then our patio would have 1 square tile in this direction, and then it would have 36 of them in that direction. So it would be a very long, narrow patio. Okay, so you can just imagine my divisions here, 36 tiles and 1 wide, or if we call that the length. So length times width is area, so we'll have an area of 36. The perimeter will be twice 36 plus twice 1, which is 74. And we'll see here as we reveal the values and fill in those yourself that here the area is going to remain constant and the perimeter will change. All right, so I've put in all the values from 1 as a length up to the maximum of 36, and there's some gaps here. There's some places where we can't fill in a width, because if we're going to use all of the patio tiles, we can't get a side length of 5 or 7 or 8 or 10, because those aren't multiples that or those are not factors of 36. And if we want to use up all the material, then we will omit those. If we wanted to use up close to the amount of material, we could probably use a width of 7 here. 5 sevens is 35. We could use 7 fives. 8 times 4 is 32, which is close and doesn't leaves a little bit more waste. 10 times 3, unfortunately, we'd have more waste here, 10 by 3. But the remainder of the values here are all factors of 36, and we can see here, if we reveal them all, we have 36 as being constant area, and the perimeter decreases from a maximum of 74 when we use a 1 by 36 pattern, all the way down to a minimum of 24 units, which, as we see, guess what, occurs whenever we have a square configuration of tiles. So we find minimum perimeter occurs for a rectangle when, again, the pieces are put into a square shape. All right, so here we are back in Microsoft Excel, and I've set up the patio data. 1 to 36 for the length, 36 down to 1 for the width. The areas we can calculate as before. If you remember, we can use our keypad, and we can take length times width. We can copy that down. Control V is a paste, quick option from the keyboard. Here I can, from the keyboard, is 2 times. If I actually want to write A3, I can. And you notice it highlights in blue cell A3. And I can add, no spaces required here, 2 times, and I can refer to B3. And that's also highlighted, and we get our first value. So copy that down in here, and we'll have all of our values. So there's our minimum at 6 by 6, and we have minimum perimeter being 24. Let's look at the graph of this. As before, I'm going to highlight all the values, including the header, for area, length. I'm going to go up here, and I'm going to insert a scatter chart with a trend line. Oh, that doesn't look very good. So let me pause. Okay, I realized my mistake. In this problem, or this scenario, we're graphing perimeter versus length. Obviously the area is constant, so it's a horizontal line. No surprise there. So what I want to do is reselect my length and my perimeter, and I'll make a graph from that. Insert scatter chart with a trend line. Now here, this looks a little bit odd. It's not very symmetrical, is it? Have I made any calculation mistakes? Looks good. I'm wondering about my scale. The scale is increasing by 10 at a time on the y-axis and 5 at a time on the x. Let's go back to our data. Okay, I'm not quite sure why the values aren't symmetrical. However, I do know that we've missed a lot of data here. So if I look at my ordered pairs, they look to all match. So this one here is 426, 330, 2, so those are all right. And then the only thing is it starts to increase by a little bit more because we were just looking for the factors of 36. So I think if I had put in some more data, the graph probably would look about the same. Actually, it would just be filling in more points in between. So anyway, it's not parabolic, but it certainly has a minimum, and the minimum is right here, the lowest point, which would be a length of 6 and a perimeter of 24. So on this next page of your handout, we're just going to summarize what we've seen. In the class, to do the graphing calculator work and get a little bit of practice entering data and making scatter plots on the graphing calculator. Here, just summarizing what we've seen is that when we are trying to find a maximum area or a minimum perimeter for a rectangle, this occurs when the sides form a square. All right, so it's a special type of shape that has those properties. Now, the maximum area provides the most coverage. We want to cover or spread out our garden in the greatest area. So we want greatest coverage, and occurs for a fixed Perimeter, we chose 24 1 meter sections, so the perimeter was fixed or constant, meaning that you've chosen the total length of the building materials. You're not going to go back and buy any more, you're going to use them all, so it's fixed. Now the minimum perimeter provides the least, we could say, edging, so the least distance around. I'm trying to find a different word for perimeter that applies what it would be in a building project. It would be edging. That occurs when we've already chosen the total, we could say, area of the building material, square footage, and we again fixed the area. Okay. So some restrictions which we saw on the rectangle that we were optimizing was that the first one, the length and the width, may have to be whole numbers in the case where the length sections cannot be cut. Okay, we weren't cutting those 1 meter sections, so we had to use whole multiples of 1. Another restriction might be when we want to make sure that we use all the material and we're starting with area segments or tiles. In that case, you want to have no waste, so you have to use particular factors of that area value. That may restrict us a little bit more than not being able to cut something, because we found that with a small enough section at 1 meter, we were able to use all the values from 1 up to 11. In some cases, it may not be possible to form a square. And if that ever happens, then we want to just make note that the square is the optimum shape for maximum area minimum perimeter. If we can get the length and width to be closest to being equal, then we'll accomplish the optimum properties. And if we go back to our data, we see that as we're just sort of centered around 6, 6 here, we get just close to that. We get two fairly small perimeters at 4 by 9 and 9 by 4. And if we were to go back to the garden scenario in our table, we see that just right around the square shape we get very close to a maximum area. We're just only 1 square unit off. So that's not exactly equal in value, but as close as we can find. All right, on the last page in your handout are 3 problems. Number 6, 15, and 17 from your textbook. So these are found on pages 94 to 96. So we'll go through these together and we'll solve them, and then you'll have class time to work on some similar problems. So the first one, we have fixed perimeter. So 650 feet of fencing. So we can kind of take note of that it's a fixed perimeter problem. So that would be area optimization. We have a half an acre we're trying to cover, at least. So we have to know what an acre is. And we're really trying to ask the question, does she have enough fencing? So let's first of all look up what the relationship is between acreage and feet. Okay, in the course study guide at the back of your textbook, you'll find this equivalence. Acre is only an area unit. So it only has meaning in square feet, 43,560. So half an acre would be 21,780 square feet. And we just need to know what the square footage of this rectangular area will be. So first statement I think we should make in our solution is that a square shape will have a maximum area where length is equal to the width. Now the area of a square is length squared. And if we know, in this case, that the perimeter is 650, let's off to the side work out perimeter and relate that to the length and the width. And again, as before, if we know the length or the width, we could solve for the other one. In this case, if they're equal, then we could really say that perimeter would be equal to 4 times the length. If our enclosure was a square, it'd be L on both sides. So let's calculate the length from that. So a quarter of 650 is 162.5 feet. From there, we can calculate the area as the square of that. And if we square that, we get 26,406.25 feet squared. We'll compare that to our half an acre, which is 21,780. We can see we have at least that much, so we can just make a concluding statement to finish. All right, in number 15, this is slightly modified from the textbook. The triangle problem worked out with a class in 2015 and found it to be quite challenging. We learned a lot about math, but we were quite a while to try to determine the optimum area, or perimeter in this case, for a triangle. So I'm just going to simplify this to rectangular or circular design, and she wants to have the least edging material for cost reasons. So which design should she use? So this is going to be a fixed area, which means it's a perimeter optimization. Okay, so in this setup, I'm just going to have two design patterns, number 1 and number 2. Again, statement of fact is that a square shape will have the minimum perimeter, so length will be equal to the width. From that, I can solve for the length. I know that the area is 30 square meters. That will be equal to L squared. And if I'm looking for L, then I would take the square root of both sides. So the root of 30 will be my length, and that gives me about 5.48, and that's in meters. Okay, the perimeter of a square, so just a little visual here, is 4 times the length, which would be 4 times that value is about 21.9, and that would be also in meters. Now, a circle's a circle. There's only really one way you can draw a circle, and it has a radius. It has a diameter. Area is two-dimensional property, so when we're trying to sort out area and circumference of a circle, take note of the exponent here. That tells us it's a two-dimensional property. The exponent, pi r squared, so r squared will be a divided by pi, where a is the area. Take the square root of both sides, we'll get the radius is equal to the root of the area divided by pi. So if we enter in our numbers, we have the root of 30 divided by pi, which we have on our calculator, and we can work that out. 9.55 is the approximate for 30 divided by pi. The root of that is about 3.09. Now the perimeter, in this case, I'm just going to label these A1 and P1. And so A2 and P2 for matching our design numbers. So just a way we can help distinguish our calculated values. So P2, perimeter of a circle, is called the circumference, and that's 2 pi r. So we know the r value, 3.09 approximately. We multiply that by 2 and also by pi, and we get about 19.4 when we're putting in 2 times pi times 3.09. Okay, so in this case, our approximate circumference or perimeter is 19.4 meters. Well, that's obviously less than 21.9. So I just make a concluding statement that Sasha should choose the circular design. Okay, and I just included a little bit of extra information, which is that the circular design is 2.5 meters less of perimeter. So that would be good. You would save yourself some building material. Let's move on to number 17, which is the last question. It's not really a numerical problem. We have swimming pool scenario. And in this case, heat loss is important. Obviously, a swimming pool, if it's heated, surface evaporation occurs, and then the water has to be reheated as you pump in more. So the greater the area of the surface of the pool, the greater the heat loss. And for a given perimeter, which surface shape would be more efficient at retaining heat, a circle or a rectangle? So in this case, we're looking at a given perimeter, meaning a fixed perimeter. So fixed sort of deck edging tells us that we're optimizing area. Okay, so in this case, I'm going to start with the circular pool. This is actually area optimization, but we don't want the highest area. We actually want the lowest area, because the more the area, the more the the pool will cool. So we actually want to keep that in mind, that the biggest area is going to actually contribute to the greater heat loss, which is undesirable. So in this case, I'm just going to assume that the perimeter was 50 feet, so 50 feet of edging on the deck. That would give us a circumference of 50, which is equal to 2 pi r. So our radius would be 50 divided by 2 pi, which gives us about 8 feet. And if we square that and multiply it by pi, we get not the value I had before, it's 63.3. That was just the square of the radius, so it's about 199 square feet. Now there's no other possibility. If we use 50 feet of deck edging, we would have to end up with an area of 199. So let's see if we can just do better than that for the rectangle. So we don't know what shape to use. We don't really want to use this square because that's the highest area for rectangle, but we don't have a lot of options, because if we use a shape that's not a square, then our length and width are different. So let's just start with the square and see if we get a number less than 199. And if we do, we know that it's definitely the rectangle that's the best choice, because obviously it'll be never any more than that maximum area. So let's assume a square. And if we assume a square, that makes the math a little bit easier. The length will be equal to the width. And if we get the length and width being equal, then the perimeter, which is 50, would just be equal to 4 times the length. From there, the length will be 12.5, and the area would be L squared, which is 12.5 times itself, and that's definitely less than 199. So if we get that maximum, this is in feet and feet squared, if we get that as a maximum, then we know we can certainly do better than that. So the rectangle area will never be more than 156.25, which means even at that, the heat loss is going to be less than the circular pool design. And from there, we could just make a conclusion that any rectangle shape will be less than the circular area. Okay. Okay, so moving on in class, we're just going to be wrapping up this section with a little bit of practice with a partner, some questions on your own choice in 12 or 13, and feedback question number 16 will be completed and submitted. These questions are found in your textbook in and around page 94. See you tomorrow.